Today, I would like to discuss deterministic classification techniques. Yesterday class, we had a discussion on introduction to pattern recognition, template matching, feature-based approach. So now, what are the techniques that are available under the classifier? The concept of pattern classification is expressed in terms of the partition of feature space, that is mapping from feature space to decision space. Suppose when we have n features measured from each input pattern, each set of n features can be considered as x, called as a feature vector, or it become a point when it is represented in n-dimensional feature space, denoted by sigma x. The problem of classification is to assign each possible vector or a point in the feature space to a proper pattern class or object or label. Let omega 1, omega 2, and so on, omega m, or m possible pattern classes to be recognized. Also, consider capital X as feature vector, where x1, x2, and so on xn are features or measurements. So now, the block diagram is a classifier. At the left side, there is a feature vector, and there are discriminant computers called d1 of x, d2 of x, and so on, dm of x. dm of x. After calculating discrimination functions, all values are fed to maximum amplitude detector to find maximum value of discrimination function and its path. Let us say d2 of x. It has the largest value and identified by maximum amplitude detector, and detector makes a decision in favor of omega 2. The discrimination function is expressed as di of x greater than dj of x, where ij takes 1, 2, and so on, m, I not equal to j. Decision boundary between regions. All regions are mutually exclusive. The difference between discrimination values is equal to 0. Next, the problem of classification is interpreted as the partition of feature space into mutually exclusive regions. Each region corresponds to a particular pattern class. Decision boundary where di of x minus dj of x equal to 0. So below an example of a partition in a two-dimensional feature space where x1 and x2 two features. There are two classes. One class represented by circle, other class represented by cross. There is a curve which is called a decision boundary. Above the decision boundary, we will say that one class. Below the decision boundary, other class. Example, we can say take it as a apple and oranges. So in order to classify these two classes, so the features may be weight and color. Weight and color. Now, under deterministic classification techniques, linear discriminant functions. When we express features as a linear combination of linear combinations, so linear combination of featured measurements x1, x2, and so on, xn is selected for di of x. So where di of x equal to sigma k equal to 1 to n omega ik xk plus omega I comma n plus 1. So where omega 1, omega 2, and so on, omega m are m possible classes. The decision boundary between regions in feature space associated with omega I and omega j is di of x minus dj of x equal to sigma k equal to 1 to n omega k into xk plus omega n plus 1 equal to 0. This is also called hyperplane equation. So where omega k equal to omega ik minus omega jk and omega n plus 1 equal to omega I comma n plus 1 minus omega j n plus 1. So we need to calculate these weights. Then only we can go for decision boundary expression. Now, so the below block diagram represents the linear discriminator computer. So where n features x1, x2, and so on xn plus 1 are fed to a discriminator system. So where wi1, wi2, win, and win plus 1 are all weights. So when we linearly combined produces discrimination function di of x. So where we need to calculate d1 of x, d2 of x, and so on dm of x, all are m distinct discrimination functions. So after calculating, so where we need to find maximum discriminator, so respective class, we can confirm for the given input features. Input features. In case of m equal to 2, very simple threshold logic device. So in order to make a decision between two classes. So below block diagram represents a linear two-class classifier. So the first one is feature vector and followed by difference weights. So where we calculate d of x, d of x. So d of x is compared with 0. If it is greater than 0, we'll say that to 1. Otherwise, it is minus 1. And another one is minimum distance classifier. So it is based on the distance between the input pattern and the set of reference vectors or prototype points in the feature space as the classification criterion. It's a very simple and popular one, easy to implement. By using Euclidean distance expression, one can find the distances between 2 points. Suppose there are m reference vectors R1, R2, and so on Rm. And we can define a minimum distance classification scheme with respect to R1, R2, and so on Rm is to classify the input pattern X as from omega I. So that is X is mapped to omega I if modulus of X minus Ri is the minimum. So after calculating the absolute value between X and Ri, so among all values, we will select the minimum and the respective reference vector. Based on the reference vector, one can decide the class. So this is about the minimum distance classifier. So this is one of the example one can understand very easily. There is a plane and it is partitioned into 4 regions. Region 1, region 2, region 3, region 4. So it is a 4-class problem. For every class, there is a center point. Whenever a new point is represented in a plane, so here the new point denotes the cross. So what we do here, so we find the distances between the input pattern and center of each class. So center of each class, so say D1, 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 D2, D3, D4. So like this, we calculate 4 Euclidean distances. So among 4 distances, select closest distance. From this, classifier makes the decision in favor of class 1 for this example. So it is a 4-class classifier. The same concept one can extend it to 8 classes, 16 classes, and beyond. So, but for all these, so the distance calculations is the main criteria. Now, piecewise linear discriminant functions. So why we go for piecewise linear discriminant functions? So when compared to linear discriminant functions, so where we have a only one straight line, it separates two classes. But uh, in reality, so it may not work always. Where we need multiple lines, multiple orientations. So when we want multiple lines to make the classes very clear to name. So like here, there are two classes. So cross represented by one class and rectangular boxes represented by other classes. So we need four joint lines in order to separate this. So in this application, one can go for piecewise linear discriminant functions. So when we combine all differences, uh, so the minimum distance reference vector and respective class is assigned to input pattern. This is the idea of piecewise linear discriminant function. The last one, polynomial discriminant functions. Those who are studied machine learning, they know very well why we go for polynomial regression. So in reality, it is not always to have a relationship between the variables is linear. So when we notice the relationship between the variables is not linear, then one can prefer polynomial discriminant functions. So now the rth order polynomial discriminant function is expressed as di of x is equal to omega I1 f1 of x plus omega I2 f2 of x plus and so on omega IL fl of x plus omega IL plus 1. So where fj of x is equal to xk1 power n1, xk2 power n2 and so on xkr power nr for k1, k2 and so on kr 1 to n and n1, n2 and so on nr are 0 or 1. So when we substitute values in this expression, so where we can expect the terms x1, x2, x1, x3, x1, x2, x3, and so on. The order of the terms, second, third, or fourth, even higher order, one can prefer in order to have a curve-shaped decision boundary. It is not a straight line. Different types of nonlinear curves. So when we require, so it's better to go polynomial discriminant function. So the block diagram represents quadratic discriminant computer where x1, x2 and so on xn are feature vector. Quadratic processor means, so we need to create artificial features. So those are called f1, f2 and so on fl. Then these artificial features are applied to weights wi1, wi2, wil, or wil plus 1. So then we can find the discriminant function. From the discriminant function, so maximum discriminant detector identifies the largest discriminant function and its a path. Based on that, one can classify the given input pattern into respective classes. So with this, I will stop the presentation. Thank you.